We'd like to talk about energy conversion in circuits. So let's first consider a seed of EMF. And in this circuit, we'll just have a resistor. So this is some type of load. That resistor may even be something like a light bulb with a filament in it. Now, when we talk about power through a potential difference, remember that when you have the change of potential energy, when you move a charge, let's call it delta Q, across a potential difference delta V, represents the change in electrical potential energy. And the rate of changing electrical potential energy is what we call power. And if we divide everything by delta T, delta V, and we take a limit, which I'm not writing out here, this just becomes current times the potential difference. And that's what we mean by the electrical power generated. You can think of it this way, is that if you have something like a battery or a wire, power can be put into the system or it can be dissipated in the system. Let's look at two examples. Let's begin by examining a battery. So in a battery, we have an EMF, and this is an ideal battery. And so what we can refer to is the power that the battery is putting in is coming from the electromotive force. Remember, electromotive force, that's some non-electrical force that's moving charges against the electric field. That represents the current that's running from the battery and times the EMF of the battery. Now, if the battery is discharging, then the battery is putting this amount of energy power into the system. And if the battery were charging, this would be the power that the battery is storing. So that's our first example. The second example is, let's look at a resistor. And we have a current in the resistor. And remember, current flows from the higher potential side to the lower potential. And so we can talk about the, let's call this V minus and V plus. Then when we have a battery connected in a circuit and current is running in this circuit, there is the electric field in the circuit is doing work on the charges. And the rate of doing that work is the power given by, so here, this is the power in the circuit or in the resistor, is given by the current times the potential difference, delta V. Now, this conversion of chemical energy, if it's a chemical battery, into electrical energy is the first step in the conservation. So what we could say is that the energy of the battery is equal to the energy in the resistor, and we have something like I times EMF equals I delta V through the resistor. And remember, from Ohm's law, in a resistor, this is I times IR, and if we cancel the R's, we get our circuit equation, which is just energy conservation. Now, let's think about what's happening in the conversion. As we know in a resistor that when electrons flow through the resistor, they're being accelerated by the electric field. That's the electrical work. So our first conversion is chemical energy goes to electrical energy. We are accelerating charges. Now, in the lattice of the resistor, there is collisions, and the lattice starts to vibrate. And what we see is that there's a dissipation of that electrical energy into what we refer to as thermal energy. This is the energy of vibration in the lattice. That means thermal energy means increase in thermal energy, the wire gets warmer.